At this point in the chapter, we've become pretty good at spotting our intermolecular attractions and having some idea of what they're going to do to some physical properties, like boiling points, freezing points, how easily it is to get it one away from its neighbor, that kind of thing. Well, what can we do then to pivot and talk more about what's going to be happening as we add and subtract motion, heat energy? That's going to be where we can actually build some of the thermochemistry back in and start thinking about not only the stickiness of our molecules, but when they get overcome by having too much kinetic energy. In other words, by heating up the molecules enough to overcome whatever stickiness there was. Now, the obvious one to talk about there would be freezing and melting. In other words, the heats of fusion, remember, heat of fusion is going to be our freezing and melting processes. Heat of vaporization is going to be our boiling or condensing processes. So let's start out with something like butane. Now, if you've ever seen a butane lighter in your life, you probably saw that there was some liquid in there. But I'll point out that it was a liquid for an extra trick. We were able to keep it liquid because we had it under pressure. And by having it under pressure, we kept it sticking to some of its neighbor at least often enough. And we'll come to that idea later in this chapter again. But we also know that butane, the moment you open the valve, it immediately evaporated and started gushing out. And if you managed to hit the sparker at the same time, you got a flame as you burned your butane. Now, it turns out that it's going to be very easy to melt solid butane. It only takes 5 kilojoules per mole to do that. And we know that's a pretty wimpy amount of energy based off what we learned in thermochemistry. Now, when we talk about heat of vaporization, how much energy did it take to get from liquid to gas phase, or vice versa? That was a little bit more energy, but it's still not a massive amount of energy as things go. Now, if we need a quick reality check on that, let's look at water. To get water to melt, we have to give it 6 kilojoules per mole. So, not much more than we had for butane. And then to get from liquid to gas phase, we had to give it about twice as much energy to get it to boil. Now, of course, there's going to be a whole lot of temperature change in between as we warm up our liquid water before we boil it. So there's a whole lot of temperature change between freezing point and melting point. This is what's happening at the freezing and at the melting point. We still have energy in between. But let's take a look at what happens with our intermolecular forces and actually map them together. So we have diethyl ether. Notice that here we've got our carbons and hydrogens on one end. We know carbon's our central atom. So the only thing we have to worry a lot about, I'm actually going to draw this slightly upside down compared to how I usually do it, is going to be this piece here in the middle. We have our bubble of electrons down there. We have our 2 carbon oxygen bonds sticking up here. And of course we have the rest of the molecule off on these sides. But we know those aren't polar, being all carbons and hydrogens, so we're not going to worry about them for the moment. Carbon is less electronegative than oxygen. Overall, my polarity is going to be something like this. So it's going to be a polar molecule. When we're talking about it sticking to its neighbor, in other words, how sticky is it to stay in the solid phase, we're going to consider this dipole compared to its neighbor. In other words, this would be a dipole-dipole interaction. Now, that's going to be reasonably strong, but not as strong as what we see for water. Water is going to have hydrogen bonding, which is the specialized and stronger version of dipole-dipole. Now you might say, well, wait a minute though, how come our enthalpy of fusion, the energy needed to melt it, and in other words, get it away from its neighbor, overcome the stickiness, why is it smaller? And the answer to that is, don't forget, you can have more than one kind of stickiness. It's true that the water is more sticky in the sense of it has hydrogen bonding. But the diethyl ether also has an extra, 12 atoms. So it's got 12 more atoms in the water. So we also have a heck of a lot more London forces going on in this one. So while this one's got more hydrogen bonding, this one's got more dipole force, London dispersion forces holding it together. And so it ended up being kind of a draw. It didn't have a whole lot of change in enthalpy for the heat of fusion. And in fact, it takes just a little bit more to get the diethyl ether to melt. But the more telling one is how much it took to get from gas to liquid, liquid to gas or gas to liquid. Butane, no intermolecular attractions other than London forces, takes about this much energy. Here we have lots of London forces, and we've turned on two dipole forces here and here. That shot it up a bit. Here we turn on a total of 4 abilities to do hydrogen bonding. Look at that heat of vaporization go up. And here we've gone for the epitome, the pinnacle of intermolecular attractions, which is actually metallic bonding in this case. In fact, it's a bonding force, not intermolecular at all. When you go up into the bonding force regime, take a look at how both of those went up really dramatically. Strong intermolecular attractions will require more energy to help them get away from their neighbors, and so all of those processes will increase. Now you might ask yourself, well, wait a minute, you didn't talk about the heats of sublimation, and you brought that up in one of the other videos talking about the terminology. I want to point out, I didn't talk about heat of sublimation? Yes, I did. Because remember, heat of sublimation is simply going to be the sum of heat of fusion and heat of vaporization. Hess's law says we just add the two processes together to get our net effect. So the total here would be delta H of sublimation, and since we're under standard conditions, I'll give it the naught up there. So here you can see the exact same sort of thing, just written down as a formula. Delta H of sublimation will equal the sum of enthalpy of fusion and the enthalpy of vaporization.